During the late 19th century, the phenomenon of electricity and the notion of an electrical current, or sometimes called an electrical fluid flow, is generally a well-accepted concept since the first electric streets light being set up in London in 1878. However, the elementary conduit of electricity, the electron, and its character is not well understood by the lay person even to this day. The story of the discovery of electrons, and the unraveling of its quantum wave character, represents a monumental development in atomic physics and gave birth to a revolutionary new idea beyond classical physics, called quantum mechanics. In this video, we walk through memory lane and tell the story of how electrons were discovered, the monumental breakthrough discoveries by Joseph Thomson, Ernest Rutherford, Max Planck, Philipp Lenard, Albert Einstein, Robert Millikan, Niels Bohr, Louis de Broglie, Werner Heisenberg, Erwin Schrodinger, Clinton Davisson, and many more. As we will see, these discoveries challenged the mainstream understanding of physics rooted in Newton mechanics and Maxwell electromagnetism and led to the development of a new branch of physics for the atomic to subatomic, called quantum mechanics. Hence, these fathers of quantum and atomic physics were decorated with the Nobel Prizes. As we shall see later, the 1890s is an appropriate starting point for our story about the electrons. Coincidentally, 1890 is the year when the artist Vincent van Gogh died in France at the age of 37 after shooting himself 2 days earlier, and the 19th century is also a period referred to as the Britain's imperial century, where the British Empire is unchallenged at sea and was dominating world trade and controlling many economies in Asia, but the beginning of the 20th century will mark a new world order defined by wars across Europe. The 19th century also witnessed one of the greatest imaginative leaps from Newtonian physics, with the unification of two fundamental forces of nature, electricity and magnetism by Michael Faraday and contemporaries, and his revolutionary idea of the concept of a force field permeating space and his discovery that light can be influenced by a magnetic field, thus setting the stage for James Clerk Maxwell in his theoretical unification of these ideas and his breakthrough publication of a dynamical theory of the electromagnetic fields in 1865. Maxwell demonstrates mathematically that electric and magnetic fields travel through spaces as waves at the speed of light. The unification of light and electromagnetic phenomena led to the prediction of electromagnetic waves beyond that of visible light wavelengths, leading to the prediction of radio waves. German physicist Heinrich Hertz proved the existence of these radio waves in the late 1880s, by using a spark gap attached to an induction coil to generate the radio waves and a separate spark gap on a receiving antenna for detecting the radio waves. The story of electromagnetic fields and waves warrant a separate video, but it suffices to say that by the end of the 19th century, Maxwell's theory has become mainstream and well accepted by the scientific community as one of the pillars of classical physics, thus also marking the end of an era and the beginning of an imminent new order in the 20th century. The late 19th century is marked by the birth of electrification in the developed world. Although Thomas Edison had invented a commercially viable light bulb in 1879, it did not receive wide adoption as electricity was still not a widely accessible and affordable commodity. Hence, in 1882, Edison constructed the first purpose-built power station in New York City, although it took few more decades before most cities and towns in America received electricity from either privately owned or municipal utilities companies. The first electric streetlight was first used in 1878 in Paris, then London, and the United States, which by 1890, there were more than 130,000 arc lamps installed as streetlights. The Italian inventor Guglielmo Marconi developed the first radio prototype in the 1890s. It functions as a wireless telegraph, where he was able to send a wireless Morse code message to a source more than a kilometer away. Stream of innovations would continue and a new cohort of scientists who specialized in electromagnetism is beginning to be in greater demand. Around 1882 to 1883, the world's first electrical engineering school was established in Germany and the United States, and this new discipline began to spread throughout universities around the world. The widespread availability of electricity has also given rise to a new generation of magician and science performers who traveled from town to town in the mid-19th century, delighting audiences with a device considered to be the ancestor of the neon sign, known as the Geissler tube. The Geissler tube consists of a glass tube where most of the air within is pumped out, and with wires embedded in opposite ends. When a high electrical voltage was then applied to the two ends, the Geissler tube would glow, and the color would depend on the gas in the tube, such as neon, argon, air, or mercury vapor, due to fluorescent. Around 1869 to 1875, the Geissler tube was evolved to allow for significantly lower pressure, from 100 Pascal in the Geissler tube to 0.1 to 0.001 Pascal. This technology was invented by English physicist William Crookes and others, thus it is also called the Crookes tube, although it is more commonly known as the cathode ray tube by the lay person. As the name implies, the cathode ray tubes produces bright rays, while the Geissler tube produces a colorful glow that filled the tube. As we will find out later, these cathode rays are beam of electrons being ejected from the cathode and attracted towards the positively biased anode end. The much lower vacuum pressure in the Crookes tube allow for the electrons to travel the whole distance across the tube, while in the Geissler tube, the electrons only travel a minute distance before hitting a gas molecule, thus the result is fluorescence of the gases across the tube. The invention of the cathode ray tube set the stage for the discovery of electrons, and we will unfold the story a minute later. The Geissler tube also enabled the development of spectroscopy, which is the study of spectral lines emitted or absorbed by substances, which is a fundamental tool in the study of physics, chemistry, and astronomy. Many scientists have been investigating the emission of light from hot atomic gases and solid objects, and most notably, the experimental spectroscopy work by the German scientist Gustav Kirchhoff. He found that low-density gas, when they are excited, will emit light at specific wavelengths, and producing a distinct emission spectrum for each species of gas. There is no explanation for why, since discrete lines appear in the emission spectra of gases at that time, and as it turns out, whose explanation would require a new kind of model beyond known classical physics at that time. More about this very soon. Variations of these tubes also led to the development of fluorescent and neon lighting, the X-ray machines, modern cathode ray tubes in TV, oscilloscope, and display devices. Since the cathode ray was produced by applying a large electrical voltage between the cathode and anode, you would guess that the cathode ray is obviously a current of electrons. However, back in those days, the idea of an electron is very alien. It was unclear if the cathode ray was some form of an electromagnetic wave, or a beam that is material and has mass. There were also beliefs that the cathode ray arises from the ether. Most notably, to verify if these cathode rays are charged particles, Hertz experimented with placing charged electric plates close to the cathode ray to deflect the beams, but failed in doing so, leading him to conclude that the beam is not charged. It turned out that the electric force in Hertz experiments was just too weak to record any beam deflection. It took the seminal research of a British professor, Joseph Thomson, in the Cambridge University's Cavendish Laboratory to finally resolve this mystery during the 1890s. He began his first experiment by investigating the influence of a magnetic field on the cathode ray. If the cathode ray is charged, then the magnetic field would exert a magnetic force on the beam, which is given by the electronic charge of the particles multiplied by its velocity in the magnetic field, as given in the yellow box. This magnetic force would produce a centripetal force, and cause the beam to deflect, with a radius of curvature r, which is proportional to the particle mass and velocity, but inversely with the magnetic field and electronic charge, as shown in the green box. In the experimental setup as shown, the cathode ray is fed into the bell jar, indicated by the blue dashed circle, where a magnetic field is being applied. Hence, if the cathode ray is charged, it would be deflected within this bell jar, and the sign of the charge would determine the direction of its deflection. Thomson placed an outlet extended into an elongated tube, allowing the deflected cathode ray to be fed into an electrometer anode. Indeed, Thomson did observe the bending of the cathode ray into the electrometer, confirming that the cathode rays as negatively charged particles. Next, Thomson decided to investigate further with another follow-up experiment. This time, he decided to also attempt to deflect the cathode ray with an electrical force, using parallel electric plates as shown. Unlike earlier attempts by Hertz, Thomson was able to get the beam to deflect with enough electrical voltage across the plates. What Thomson did subsequently lead to a monumental discovery of the electrons. He decided to set up both magnetic field and electric field within a small middle region of his cathode ray tube as illustrated. The electric field produces an electrical force given by the electronic charge multiplied by the electrical field across the plates, while the magnetic field produces a magnetic force given by the product of the electronic charge, the particle velocity, and magnetic field. These expressions are given in the orange boxes. Thomson's idea is to set these two forces such that they act in opposite directions, and then modulate the magnitude of electric and magnetic field, such that the beam is left undeflected. In other words, the electrical force is balanced with the opposing magnetic force. Under this condition, by equating the two forces, One can show that the particle velocity in this middle region of the tube where the forces are being exerted would be the electric field divided by the magnetic field as shown in the green box. Knowing the distance between the cathode and this force region, L, and using well-known Newtonian kinematic equations, one can then determine the acceleration of the particle A, given in the blue box, expressed in terms of the velocity v and the length L. Since the electrical force is given by mass multiplied by acceleration, we then obtained an expression of the electronic charge to mass ratio of the particle, given to be the ratio of acceleration to the electric field. This simple procedure allows Thomson to extract charge to mass ratio. Thomson boiled down the findings of his 1897 experiments into the following. First, the cathode rays are comprised of charged particles, which he also called corpuscles at that time. Second, he determined that the charge to mass ratio of the corpuscles are more than 1,000 times smaller than that of hydrogen ions. His estimate is somewhat off from the actual ratio of the proton to electron mass of 1836, due to experimental imprecisions at that time. Third, the charge to mass ratio is the same irrespective of the cathode or anode metals used. Thus, this points to these corpuscles as being an integral constituent of every atom of elements. Note that the concept of atom has been introduced into chemistry and the chemists had already been populating the periodic table, with the first version of periodic table published by Dmitry Mendeleev in 1869. Chemists assigned hydrogen with a weight of 1, and then used compounds of hydrogen to determine the relative weights of the other elements, a methodology initiated by John Dalton. Thomson's experiment marked the first experimental evidence into subatomic structure, which certainly monumental feat in science. Interestingly, these corpuscles identified by Thomson are named electrons only sometime later, as proposed by the chemist Stoner. The Thomson plum pudding model of the atom was thus being proposed, where the atom is pictured to have negatively charged electrons embedded within a positively charged soup. Thomson's plum pudding model would become the prevailing model of the atom for a decade before the next breakthrough in our understanding of the atom. We shall take a slight detour to set the stage for another monumental breakthrough in our understanding of nature. This time, her fingerprints are being revealed in the emission spectra of hot gases and solids. Scientists have observed the discrete emission spectral lines of incandescent gases, example that from the Geissler tubes. Here we show the emission spectral lines for hydrogen. In 1885, Johann Balmer, a Swiss high school teacher, noticed that these spectral lines can be described by the formula in the green box, now known as the Balmer series. Lambda denotes the emission wavelength, and n are integer numbers larger than 2. It was documented that Balmer arrived at this formula through sheer persistence and probably luck, as he had been studying these spectral lines for years. However, Balmer formula does not capture all the main spectral lines of hydrogen gas. Other sets of spectral lines have been observed, which follows different formulae such as the Lyman series, Paschen series and so on as indicated in the table. In 1888, the physicist Johannes Rydberg generalized Balmer's equation to account for all the transitions of hydrogen, hence all the known transition series in the table, and this is now known as the Rydberg formula, as shown in the blue box. Although the Rydberg formula was able to successfully describe the positions of the hydrogen emission spectral lines, a physical theory behind this observation was lacking. It remained one of the unsolved mysteries in classical physics. Hot objects, just like hot atomic gases, also exhibits an emission spectrum. Scientists are interested in black body, which is an object that absorbs all radiation falling on it. Hence, the black body is an ideal system for the study of emission spectra from hot body. The black body spectrum was somewhat well explained in the longer wavelength limit by classical theory as shown. However, classical theory predicts that an ideal black body at equilibrium will emit an unbounded quantity of energy in the ultraviolet range, which is of course nonsensical. Thus this problem is called the ultraviolet catastrophe. Max Planck, a German theoretical physicist, decided to undertake this challenge to come up with a new theory. He made several attempts before finally succeeding in arriving at the correct formula in November of 1900. The first new addition to his theory is the use of statistical mechanics, by relying on the Boltzmann statistical interpretation of entropy and a derivation of a more accurate statistical distribution. The second and central assumption to his new derivation is the postulate that the electromagnetic energy can only be emitted in quantized form, in multiple of an elementary unit energy equal to the Planck constant multiplies by the frequency. Here, we see how the discreteness of energy is a recurring theme, both here and in the emission spectra of gases such as hydrogen. Physicists now call these quanta of energy, or packet of energy, a photon. With this new physical theory, Planck is then able to remove the ultraviolet catastrophe. However, a lingering question remains for Planck: are there any physical basis for his hypothesis of the quanta of energy? In 1887, while the German physicist Heinrich Hertz was demonstrating the existence of radio waves as predicted by Maxwell, he noticed that when ultraviolet light shines on two metal electrodes with a voltage applied across them, it introduces an anomaly in his experiment, altering the voltage at which sparking occurs. Hertz did not have an explanation for this phenomenon, but it was clarified in 1902 by another German physicist, Philipp Lenard. He demonstrated that the ultraviolet light releases electrically charged particles from the metal plates, and that these particles are identical to electrons, which was the same electrons discovered by the British physicist Joseph Thomson in 1897. Several aspects of the photoelectric phenomenon are not compatible with classical physics, which describe light as a wave. An inexplicable observation is that the maximum kinetic energy of the released electrons does not vary with the intensity of light as according to the wave theory, but was instead proportional to the frequency of light, f, although the intensity did determine the number of electrons being ejected from the metal, measured as an electric current. The measured electrical current will be proportional to the number of electrons multiplied by the velocity of these electrons. This led Albert Einstein to formulate a new corpuscular theory of light, in which each particle of light, or being called photon, contains a fixed amount of energy, just as what Planck has postulated earlier. When photon with energy above a certain critical threshold hits the metal surface, it will be able to knock electrons off that was previously bound to the metal. That threshold energy is also the work function of the metal. Each particle of light, called photon, uses its energy to overcome the work function of the metal to break the electron loose, and then transfer the rest into the kinetic energy of electrons, as given by the equation in the yellow box. Although Einstein's model described well the photoelectric effect, the idea was sufficiently radical. The idea that an electromagnetic wave that impinged on the metal is also at the same time a particle which carries a packet, or quanta, of energy, is mind-boggling, and thus it took several years of further experimental verification and extremely accurate measurement by American physicist Robert Millikan before Einstein was finally awarded the Nobel Prize in 1921 for explaining the photoelectric effect. 1905 turns out to be the most productive years of Einstein's career, where he wrote 4 papers that would change the way we think about our universe. The photoelectric effect paper, where he introduced the revolutionary idea that light is composed of both wave and particles, being one of them. The second paper is titled On the Movement of Small Particles Suspended in a Stationary Liquid, as required by the molecular kinetic theory of heat, which laid the foundation that matter is composed of atoms and laid the foundation for statistical physics. The third paper is titled, On the Electrodynamics of Moving Bodies, which presents Einstein's famous theory of special relativity, which also precedes his subsequent monumental work in general relativity. The last paper is titled, Does the Inertia of a Body Depends on its Energy Content? In this work, Einstein elucidated on the equivalence between matter and energy, as summarized in the equation in the yellow box, where E is the total energy of the particle, m0 is its rest mass, c is the speed of light, and p being its momentum. Thus, the total energy consists of a part that arises from its rest mass, and another part due to its momentum. If one applies this equation to that of a photon, which has 0 rest mass, thus m0 will be 0, then we arrive at the momentum of the photon, which is given by its energy divided by its speed. Thus, if the photon carries a quantum of energy, it will also carry a quantum of momentum. Keep this equation at the back of your mind, as we shall see it again later in this video. In 1909, nuclear physicists Ernest Rutherford and his graduate students, Eugene Marsden and Hans Geiger, who will later invent the Geiger counter, performed a series of experiments in which gold foil is bombarded by heavy, fast-moving subatomic particles known as alpha particles. As shown here, alpha particles are composite particles consisting of 2 protons and 2 neutrons tightly bound together, produced during a form of radioactive decay. Matter during this time was thought to be rather smooth and evenly distributed, even if it consists of atoms, much like Thomson's plum pudding model, where the positive charge is the pudding, and the electrons are plums, or more like raisins. However, what he observed in his experiments was quite unlike this plum pudding picture. He observed that most of the alpha particles went through the gold foil with little or no deflection, which he can see them as they hit the fluorescent screen at the opposite side. A few of these particles get deflected with large angles, with only very few of them get bounced back to the source. Rutherford, when recalling the discovery, remarked it was quite the most incredible event that has ever happened to me in my life. It was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you. To reconcile with his observations, Rutherford must discard the Thomson's plum pudding model, and instead propose the solar system model of the atom. In this model, as depicted here, the atom is mostly empty space, which contains a very small but incredibly dense nucleus, but even smaller electrons. Subsequent theoretical analysis reconciled the observed angular spread of the scattering experiment, which corroborates with this solar system picture with a heavy charged center called nucleus. However, as it turns out, Rutherford did not have the final word on this matter, and another revision to the atomic model is in order. Can the electron charge be measured, and what is that value if it is a fixed quantity? This is a question that Robert Millikan, a physicist at the University of Chicago, is determined to find out. He carried out a series of experiments from 1908 to 1917, where he studied the behavior of oil droplets in an oil chamber as shown in the left figure, a picture taken of Millikan's original oil chamber where he performed this seminal experiment. The experiment, as depicted on the right, consists of first spraying very fine oil droplets into a chamber. These oil droplets would acquire some static charge due to the friction of being sprayed into the chamber. In the middle of the chamber, he positioned a positively charged metal plate, and a negatively charged one at the bottom. An outlet on the positive metal plate would then allow some of the oil droplets to descend towards the bottom plate. These droplets will experience the gravitational force which pulls it down, and an upwards electric force on the negatively charged oil droplet. Uncharged droplets will fall to the bottom. Through balancing these two forces, by tuning the voltage being applied across the two plates, Millikan can suspend oil droplets in the air, as viewed through his viewing microscope. He will seek to find the smallest voltage that enable the suspension of the oil droplets, where he can observe through his microscope, and this would correspond to the situation where the oil droplets each carry an electron. Knowing the mass of each oil droplets from a separate experiment, Millikan was then able to deduce the charge of an electron to be 1.602 times 10 to the power of minus 19 coulombs. This is the smallest charge he observed in his experiment, and these charges occurs in multiple of this elementary charge, thus providing irrefutable evidence that the charge of an electron is the smallest and most fundamental unit of charge in the universe. This experiment is 11 years in the making, and certainly monumental in its discovery, which eventually won Millikan the 1923 Nobel Prize in Physics. In 1913, a Danish physicist Niels Bohr published a paper and pointed out an inconsistency with the Rutherford model. An orbiting electron in the Rutherford solar system model of the atom would experience a centripetal force and hence an acceleration. According to the already well-established Maxwell's electromagnetism, such an accelerated charged particle, such as an electron, must also radiate electromagnetic energy, which means the electron would then have to lose its energy and spiral into the nucleus, thus eventually causing the atom to collapse. Thus, a revision to the Rutherford model is in order. Niels Bohr proposed that electrons move around the nucleus but only in prescribed orbits, as depicted in the left figure. Each of these orbits labeled n equals to 1, 2 and 3 has a fixed energy, where the orbit closer to the nucleus has lower energy, and vice versa. If electron transition from higher energy orbit 2 to 1, it will emit radiation, but absorbed radiation if the electron transition to higher energy instead. Of course, if the electron is in the lowest energy state, or the ground state, it will not be able to emit any radiation. Impressively, the Bohr atomic model of discrete energy levels can account for the discrete emission spectra observed in hydrogen gas, fully accounting for all the different series of the emission spectra, or the Rydberg formula, as shown in the right figure. Not only did Bohr provided a physical model for the structure of the Rydberg formula, but it also provided a justification of the physical constants in this formula. Of course, Bohr atomic model would also provide a physical basis for Planck hypothesis for the quanta of energy, which is crucial in the explanation of the black body emission and the photoelectric effect by Einstein. Despite these achievements, there are still fine structures in the hydrogen emission spectra that cannot be explained by Bohr, not to mention the spectra of other gases beyond hydrogen. Quantum physics is at a juncture where precise theoretical tools must be developed so that more complicated concrete calculations can be made. This will be known as quantum mechanics. Unlike Newton mechanics, which is based on the application of Newton's laws of motion, quantum mechanics will be based on the application of the principles of quantum physics, and its birth was just being witnessed with the advent of Bohr's discrete energy model for the atom. By this time, scientists had already come to accept that light behaves as waves, manifesting wave properties such as diffraction and interference, but also behaves as particle known as photon in other cases, revealing discrete properties such as quanta of energy. The characteristic of the light wave, such as its frequency f, is related to the photon energy via the Planck constant h, as in the yellow box. It is also common to express this Planck relation in terms of the reduced Planck constant h bar, and its angular frequency omega. In addition, the characteristic of the light wave, this time its wavelength lambda, is related to the photon momentum via the Einstein relation as we previously derived. Alternatively, we can also express the momentum p as the product of the reduced Planck constant with its wave number k. Around 1923, a French physicist Louis de Broglie began to ask if these two relations, which relates light wave characteristics to its particle properties such as energy and momentum, could be a more general property of all matter. In other words, could matter such as electron also exhibit wave-like behavior? Unlike sound wave, water waves, or electromagnetic waves for the case of light, what waves are these matter waves? It was probably unclear at that time what physical waves de Broglie was referring to, but we now know these are quantum mechanical probability waves. In his thesis, de Broglie argued that matter would also exhibit wave-like behavior, just like photon, a hypothesis that later proved to be correct by experiments on electron diffractions, which we will discuss soon. Unlike the case of photon, electrons considered here are not relativistic. Note that quantum mechanics, at least what we are dealing with at this stage, is a non-relativistic theory. Hence, the energy of the electron is just the Newtonian kinetic energy. If the electron is a wave, then we know how to compute the group velocity of a wave, as defined as the derivative of omega with respect to k. Using the Planck relation, assuming that this relation holds true for matter waves, then allow us to obtain an expression of omega in terms of momentum p, which then allows us to derive at an expression of the group velocity as shown. After some algebraic manipulation, we can arrive at the equation we have shown in previous slide, which is the momentum p equals to the Planck constant divided by the wavelength lambda, as shown in the blue box. This wavelength lambda is called the de Broglie wavelength. As we will show in the videos on quantum mechanics, this de Broglie relation can be proved rigorously from quantum mechanics through the quantum mechanical translation operator. For now, this heuristic derivation would suffice. Writing here again the Planck relation and the de Broglie relation, we see a very delightfully beautiful symmetry between these two relations. In the former, the particle energy is related to its wave-like character frequency or period. In the latter, the particle momentum is related to its wave-like character wave number or wavelength. In other words, energy is to time, just like momentum is to position, and encapsulate the particle-wave duality in quantum physics. As we shall see later in quantum mechanics, the energy and time are what we call conjugate quantities, just like momentum and position, and will be a recurring and fundamental theme. These developments in quantum physics, cumulating in the powerful insights of de Broglie wave-particle duality, sets the stage for the assimilation of these new ideas into the formalism for quantum physics, called quantum mechanics. The first step in the formulation of quantum mechanics began with Werner Heisenberg in 1925. A key starting point by Heisenberg is to recognize that quantum physics is a theory focused on measurable observable quantities. In other words, instead of focusing on unmeasurable quantities like the orbit of electrons in an atom, he set forth the mechanics of computing measurable quantities like the electron transition rates. Another of his inspired ideas was that the electron position x and momentum p do not behave as numbers, such that their multiplication is not commutative. In other words, x multiplied by p is not p multiplied by x. It was Max Born who later recognized these x and p operators are matrices. These led him to discover the non-commutative relations between the momentum and position observables as shown, which also led to the result of the Heisenberg uncertainty principle. Max Born, Werner Heisenberg, and Pascual Jordan collaborated and contributed to the matrix formulation of quantum mechanics. Paul Dirac, who became aware of Heisenberg's work, soon realized the crucial role of the non-commutative relation and recognized it to be the defining feature of quantum mechanics. He showed that the classical counterpart or limiting form of the commutator of two quantities was their Poisson bracket, which appears in the Hamiltonian form of classical mechanics. Dirac also invented the Dirac-Bra and Ket notations that is still commonly used in modern quantum mechanics. Dirac's key papers on the formulation of quantum mechanics were published before the end of 1925. Erwin Schrodinger in Zurich was also independently developing the wave mechanics approach, inspired by Louis de Broglie's concept of matter waves. His work led to a series of landmark papers from 1925 to 1926, where many key postulates in modern quantum mechanics are being described, such as the notion of quantum state of the system, a complex wave function, the Schrodinger equation of motion, and the superposition principle. Schrodinger also showed the equivalence of the matrix and wave mechanics in his paper entitled On the Relation of the Heisenberg-Born Jordan Quantum Mechanics to Mine. By 1927, the formulation of quantum mechanics was almost fully fleshed out, marking the beginning of a new chapter in modern quantum physics. The discussion on the success of the applications of quantum mechanics will be the subject of another video. For viewers who are interested in the formalisms of quantum mechanics, we refer you to a series of videos in our quantum mechanics playlist. So, what wave does de Broglie refers to in his idea of a matter wave? This turns out to be the quantum wave functions. We shall briefly introduce the notion of quantum wave functions here, but referring the viewers to our other videos for a more pedagogical treatment on this subject. In classical mechanics, the position and momentum of the particles are all we need to determine the future and past configuration of the system. Hence, classical mechanics is a deterministic theory. Quantum mechanics, on the other hand, is probabilistic in nature. The state of the electron is now being represented in terms of the quantum wave function, psi, where its modulus square is the probability function. The probability function tells us the probability of finding the particle in real space or momentum space, where the two are related via a Fourier transformation. Thus, in quantum mechanics, the electron wave function contains all the information about the state of the electron. Thus, when we say electron is a wave, we are referring to the electron wave function in the quantum mechanics sense. The electron de Broglie wavelength is given by the Planck constant divided by its momentum. Consider an electron moving at 1/100th of the speed of light, and plucking in the mass of a free electron. That would yield us a de Broglie wavelength of 2.4 angstrom, which is of the same order as lattice constants of most metals. In other words, electrons passing through high-quality metals, where the quantum wave nature of the electron sets in, should manifest some wave phenomena such as diffractions and interference as we have seen for the case of light. In 1927, American physicists Clinton Davisson and John Germer were experimenting with electron beams. When the electron beams are being directed towards a high-quality nickel crystal, they observed multiple sharp beams of electrons emerging from the other end of the nickel. A precise comparison of the directions of these scattered electron beams and that predicted by quantum mechanics confirms that the electrons were diffracting off the individual nickel atoms, interfering with each other as they leave the surface, thus producing an interference pattern. This experimental demonstration of the quantum wave nature of electron was also independently studied by Joseph Thomson, and they were both being awarded the Nobel Prize in Physics. In later years, various groups were also able to demonstrate similar electron wave interference patterns in a double-slit setup, just like what Thomas Young observed a century ago with light. From the discovery of electrons particles by Thomson in 1890, to the observation of electron diffractions by Davisson and the successful formulation of modern quantum mechanics in 1927, a new chapter in modern physics has begun, where quantum mechanics will become arguably the most successful quantitative theory ever produced and forms the foundation for designing modern-day computing and communication devices. Quantum mechanics also challenged our very preconceived notion of what reality means. Is the sun not there when you are not looking? Einstein asked. Can the cat be both dead and alive? Schrodinger asked. These philosophical questions are at the heart of the 1927 Solvay conference, which represent the pinnacle of the debate on the interpretation of quantum mechanics. Despite the success of quantum mechanics in explaining and predicting a broad range of experiments to great precision, the subject of how the mathematical theory of quantum mechanics might correspond to our experienced reality remained a contentious topic with different schools of thoughts, a topic we shall venture into in future videos. Stay tuned, and subscribe, so you will be notified of our future episodes. Join our Free Science Academy Discord channel to discuss science and technology. High school students are welcome to join and post your questions, we will answer them during our free time.